This is Professor Jeff Wilkerson at Luther College, providing you an introduction to some of the material in the laboratory manual available from Kindle Hunt, Astronomers as Observers and Experimenters. So what we'll do is we'll provide introduction to various activities and exercises in that lab manual, and today we're going to just talk a little bit about a larger concept to look for as you work through the exercises in that book, and this is observational bias. Observational bias is all around us. It's everywhere you look, and we want to start to think about how it affects how we observe the universe and the models we make of the universe, and maybe when we're able, how we can correct for known observational bias. So we'll start with a story here. When I was young, I grew up in a family that grew all of our own vegetables, lived we're relatively close to the land, tried to extract as much as we could of our living from the world around us. And one of the things that we looked forward to every spring was morel mushroom season, and we would go out and we would hunt morel mushrooms to sort of supply us with a little bit of interesting extra food in the spring. And morels, the story went, when I was growing up, that morels came in basically two categories. Whether this is true or not, I don't know, and we won't worry about that. But small gray morels and larger yellow morels. So lighter colored and larger, a little bit darker colored, grayer and smaller were the two categories. Whether there's really two categories or an infinite spectrum or whatever that is, let's not worry about that. Let's just say that's the rule that we had growing up, that there were two types of morel mushrooms. What I was also told was that the small gray morels were to be found in the woods, and they were to be found near dead and dying elm trees largely, but sort of around trees that were near the end of their lives. And you had to look pretty carefully because they're gray, they blend in, they're kind of hard to see, and they're small. And so you had to look pretty carefully for them. The bigger yellow ones also lived in those environments, but I was taught that they would also be found in open fields and grasslands. You could sometimes be walking across a meadow and there would be these larger yellow ones, so they liked a more open area, not just the shaded dark woodlands around these trees. What happened when I grew up and started exploring new spaces on my own, spaces I'd never been, and poking around a little bit, I started to find quite a few small gray morels in, or what would have been categorized as those, in trails, in open pathways, and in the fields, and exactly the kind of places where I was told that they didn't exist and that you should be looking for them in the woodlands. And what I started to realize is probably a model of the universe was built about where these types of mushrooms were based on observational bias. It's just plain hard to see the smaller, darker mushrooms in a grassland. You can see the larger yellow ones because they stick up above it, and you can see them from a long distance. And you go over and you say, wow, I wasn't expecting to find morels here in the wide open, but here they are, so let's pick them. And so when you do that enough, you end up with a model that tells you that you only find the yellow ones out in the open spaces. If you really do some close observing and some close monitoring of what's going on, you realize the darker gray ones might be there too, and your model of reality, your model of the universe was affected by this observational bias. Easier to see the larger yellow mushrooms. Now let's apply that concept to astronomy here just a little bit. So we'll take about a couple of ideas. As you work through the activity in Astronomers as Observers and Experimenters, so you have all of these exercises. As you work through them, I want you to keep your eye out for observational bias and how it affects what you're seeing, what you're plotting, and what you're measuring. And so as you work through there, every one of the exercises, it's good for you to ask yourself, is there observational bias here? Some places will point it out to you, and we'll ask you to think about it, or we'll say gather data from other students around you and look at all of the data on the board and try to figure out if you can deduce an observational bias based on that, and how would you correct for it. And so, but let's talk about one of the exercises in the lab book is asking you to plot data from an eclipsing binary star that's part of the research work that I do here with students. And so just looking at what a light curve would look like for an eclipsing binary system. Now, an eclipsing binary system is where you have two stars one in orbit around the other one. Now let's suppose these two stars, they're both in orbit around the center of mass of the system, obviously. But let's suppose that the orbit is perpendicular to the plane of the board, so that they're orbiting this way right now. And so, like, for example, in this instance, this star is coming out and that star is moving into the board. Now, if you were here observing, you would see that as an eclipsing binary. One of the stars would pass in front of the other star, dimming the light of the system, blocking light from this other star. If you were observing from up here, you would not see that as an eclipsing binary system. You would always see both of these stars wherever they were. And if you were up here observing, you for sure would always see the separation of these two stars. So what happens is this: as the separation of these two stars shrinks, as it gets closer and closer together, you can be at a pretty steep angle up this direction and still see something of an eclipse. You have to be, if these two stars are touching each other, you have to be right up here not to see that as an eclipsing binary star. Every other one of these angles would see an eclipsing binary system. The result of that is that the closer these two stars are together, the shorter the period of orbit is. So the result is it's much, much easier to detect short period eclipsing binary stars than it is long period eclipsing binary stars. Imagine two stars that are separated by a lot, and if you have this big separation, it's not really, it depends, a lot's an arbitrary number, but separated by much more, and imagine you're observing on this plane, you don't have to get tipped up very much at all before you continue to see separation between those stars and you never see an eclipse. And so you can sort of calculate what that angle is. So suppose you're observing right in the plane of this, of what we have drawn right here. And you can calculate just how much above or below this plane right here, this secondary star could be, and you would not see it eclipse. You would not see it disappear behind this other star from this vantage point. So you can calculate what that angle is right there. And the bigger this separation gets, the smaller that angle gets, and the less likely you are to observe that as an eclipsing binary. Also, the larger that distance gets, the longer the period gets, and the less frequent the eclipses would be, even if it were eclipsing. Even if it's right in your plane, and the eclipses get longer and longer and longer between them, you have a harder time seeing them. On any given night, you don't see an eclipse. You look the next night, you don't see an eclipse. You look the next night, you don't see an eclipse. You look the next night, you don't see an eclipse. But many nights are cloudy, so you're not looking every night anyway, even if you're studying this system. And it may turn out that you're only going to see an eclipse every few months, or something like that. And if you only see an eclipse every few months and it's cloudy on that night and the next night, and you're not looking the next night that there's an eclipse, you can go years without seeing an eclipse and you don't detect that that's an eclipsing binary system. So there's two reasons that make short period systems easier to detect. One is you can detect them with that angle being much, much steeper. They still at least look partially eclipsing. So you see a much bigger angle. And that angle is sort of arbitrary. It's random, and so you see a much bigger angle, and you see much more frequent eclipses. They're just much easier to detect. So if you were to go out, if you were to count eclipsing binaries in this project we have going on, we've counted 6 such systems. They all have periods that are pretty short by the standards of binary stars. Most of them have periods less than a day, and I think one of them has a period of 1.88 days, and I'm trying to remember the other one in there that has a period of up to 8 or 9 days. But we're talking about days, much shorter, hours in most cases, and days in other cases, much shorter than the period of Mercury in orbit around the sun. So these stars are close relative when you think about the separation of astronomical objects. Why? They're easier to see that way. Do we have eclipsing binary systems in our field of view that maybe have longer periods? Maybe, but maybe not, just because they don't eclipse because of that larger angle. Now, if we were to build a model on this without thinking about that, we might build a model and go out and tell the world, hey, guess what? Short period eclipsing binary stars, stars that are very close to one another, are much more common than stars that are separated by a greater amount. And that probably turns out to be not true. We can calculate what our efficiency, knowing this angle right here, being good at trigonometry and geometry like this, we could go in and calculate what our efficiency is at detecting an eclipsing binary system. How does the likelihood of it eclipsing depend on the period of orbit? and say, you know, by the time they touch, we see essentially 100% of them as at least partially eclipsing systems, down to by the time that they're separated, we see it's approaching 0% that we see. It never gets to 0, but it's approaching that direction as we move out there. And we can correct for that. Once we correct for that, then we can make a more accurate model of what the distribution of periods of eclipsing binary stars is. That's an example of observational bias. Much easier to see short period eclipsing binary stars than long period eclipsing binary stars. Another example that I'm going to give you as homework to go think about. Very common to see lists of stars that have 20 or 25 stars in them, maybe more, that are the brightest stars on the sky, and another list that are the nearest stars on the sky. Stars are put into something called spectral classification. So we classify them via a letter scheme, and maybe you know about this by now when you're watching this video, maybe you don't, maybe you'll learn about it as you work through whatever course you're in right now, if you're in an astronomy course. But anyway, you can count the number of stars that we see in each of those two groups, the nearest stars and the brightest stars on the sky in each spectral classification group. If you count the brightest stars on the sky, go out and do it. Find a list of 20 or 25 or 30 of the brightest stars on the sky and count the number of stars that fall in each of the classification schemes. O, B, A, G, O, B, A, F, G, K, and M. I've only been doing this 30 years. You'd think I'd figure out some of this. And count how many O stars, B stars, A stars, F stars, G stars, K stars, and M stars are among the 25 brightest. And then look at the 25 nearest stars and repeat. So you have the brightest stars over here and the nearest stars over here. And see how many are in each of these classifications. And you will find very different results. If you were to base your models of how common stars of different spectral classifications are only on the brightest stars you see on the sky, the stars you can walk out and see with your naked eye without optical aid on any given night, you might deduce that A and F stars are among the most common stars in the universe, in our galaxy. If you look at the nearest stars, you might deduce that M stars are the most common stars in our galaxy. Now, which of these is more accurate? It's probably a better bet, but we can't say with 100% certainty just about anything. Probably a better bet to look at the nearest stars. It's less likely that we live in a special place in the galaxy that is overpopulated with M stars relative to the rest of the galaxy. It's much more likely that we can see bright stars. These stars, O stars, are the brightest of stars. M stars are the faintest. So the stars go from bright to faint down this way. Very hard to see faint stars, very easy to see bright stars. We can see bright stars a much greater distance into the universe, into the galaxy. So we can again do a correction to say, given our limit of our magnitude limit, what's the faintest star we can see? How much more likely, how much more volume of space do we sample in A stars than we do in K stars, for example? How much more volume of space do we sample in B stars than we do in M stars? And we can calculate the volume of space that we sample. How far into space can we see each of these classifications of stars? And we can correct this and even this to start to make a better model of what the distribution of stars as a function of spectral classification is. Again, observational bias is what caused us, if we just look at the brightest stars, that causes us to think that brighter stars might be more common because we see them further. They're easier to see, like the big yellow morels, like the eclipsing binaries with short periods. So that's an introduction to observational bias. As you work through the exercises in Astronomers as observers and experimenters, and I hope you do, we'll introduce you, we'll ask you about this in a few places in the exercises, but I want you to think about it on your own. As you read it, to think, is there an observational bias here that I'm not accounting for that makes me build a model of the universe that's less accurate than it would be otherwise? So that's our introduction to observational bias. We'll have more on other activities. I hope you check it out, these video introductions, and good luck with the work, everyone.